Good morning. Today we are going to discuss the forward flight, and first we will concentrate on actuator disk theory. The actuator disk theory, or the momentum theory in forward flight, it was extended from hover to forward flight by Glauert in 1927. He proposed a modified actuator disk. Consider that the rotor is flying past, disturb all the air in the neighborhood from far above to far below. And if you remember, consider that the mass flow passing through the rotor is rho p r square and Vr, the resultant velocity. The resultant velocity is composed of the forward velocity v and the induced velocity at the level of the rotor, Vi. Writing also the conservation of the momentum, so the thrust equals with m dot multiplied by twice the induced velocity, and in this way we assumed that the wake is contracting and that the velocity down in the wake is twice induced velocity of the rotor, we obtained the Glauert formula. This formula gives the induced velocity in forward flight and is defined as the ratio, Vi defined as the ratio of thrust divided by 2 rho p r square and Vr resultant velocity. Now consider that we are in a general climbing flight and alpha d is the angle between the disk, the tip-off plane, and the velocity. You can project the velocity vector into v sinus alpha d and v cosine alpha d. Therefore, the resultant velocity would be v cosine alpha d square plus v sinus alpha d plus Vi squared. But you remember we extending the Glauert formula of the induced velocity. Substituting Vr into the formula of Vi and introducing as non-dimensional notation V bar and Vi bar, we obtained a quite simple formula which gives the induced velocity in forward flight. Vi bar square equals with 1 divided by the square of the V cosine alpha d plus V sinus alpha d plus Vi squared. This is the Glauert formula for calculated induced velocity in forward flight. How to calculate this induced velocity in forward flight? Well, the first thing is that we can simplify the Glauert formula. So, if we are going in high forward speed, induced velocity is much smaller than the forward velocity V. And in this way, if we are neglecting Vi in the Glauert formula, you get that the V cosine square plus V sinus square is V square, and the formula transforms in Vi bar equals 1 over V bar. Another approximation that is in low speed flight. In low speed flight, the angle of attack of the disk is almost 0. And in this way, cosine of alpha d is 1 and sinus of alpha d is 0. Therefore, we obtained a fourth order equation in Vi, which is depending only on the forward velocity V, and from where we can calculate induced velocity in forward flight. Observe that in a vertical climbing flight, the disk angle of attack is 90 degrees. Therefore, sinus is 1 and cosine is 0, and the induced velocity is 1 divided by c plus Vi. We can represent this calculation into a graph giving the velocity V bar and Vi bar. You can obtain that the fourth order equation, it is valid through the whole range of velocities, of forward velocities. From the v bar horizontal axis equals 2, we can use the approximation 1 over v to calculate vi. And in this way, we can calculate induced velocity for all ranges of forward speed. What is if we want to include the alpha disk in a Glauert formula? We have to calculate this angle for a certain condition. For this, we have to represent the forces in a trim condition for a climbing flight. You see that the forces acting on the rotor are the thrust, the weight, and the drag of the fuselage. If you represent these helicopter forces acting at the tip of plane, the equilibrium of them in the axis of the velocity will give you a formula for sinus alpha d, where gamma, you see, is the flight path angle. Flight path angle in horizontal flight is 0, and the sinus then is 0. Therefore, how to solve numerically Glauert equation and obtain the induced velocity? We start from knowing forward velocity. We calculate the angle of attack of the disk with the formula sinus alpha d equals with the drag of the fuselage divided by v. The drag of the fuselage can be also easily calculated knowing the weight of the helicopter. Then we calculate the v sinus alpha d, the v cosine alpha d, and we can solve again numerically the equation in vi. Generally, for induced velocity in a climbing or descending flight, Hafner represented the so-called, in a Hafner diagram, the v cosine alpha disk and v sinus alpha disk. You see here lines of constant VI bar. For example, if we know the angle of attack alpha disk and we know the forward velocity, we can calculate in this way V cosine alpha disk and V sinus alpha disk, and from here we obtain from Hafner diagram induced velocity non-dimensionalized. In this way, we obtained the induced velocity for forward flight and generalized the actuator disk theory from hover to forward flight. This ends this lecture of today.